So welcome to acids and bases. So things you need to know: define acids and bases in terms of proton donors and proton acceptors, and differentiate among acids, bases, neutral ionic, neutral molecular, strong acids, and weak acids, and based on appropriate diagnostic tests. Okay, so an empirical property are made from observations from experiments. So, for example, we can test if something is an acid or a base. So if we want to know if a lemon is an acid, we can use a litmus test and see that it turns red, and we can see that it's an acid. So the fact that it's an acid is an empirical property. So you need to know some things about acids and bases, and you've learned these in other courses. So you should know that acids have a pH above 7. You should know that they turn litmus red. You should know that they react with metals. You should know that they are sour in taste, but obviously don't taste them in the lab. And you should know that they conduct electricity. Okay. Base is pretty similar. pH below 7. They turn litmus blue. They don't react with metals. They are bitter tasting, and they are slippery. And they also conduct electricity. Okay, for neutral things, they have a pH of 7. Red litmus stays red. Blue litmus stays blue. Okay. And then there are two types of neutral. There's molecular, and there's ionic. For ionic, you're going to have a metal and a non-metal. And then for molecular, you would just have non-metals. So maybe you forget how to tell if something's a metal or a non-metal. So if we go into our data book, oops, wrong data book. And we take a look at our periodic table. I'm just going to zoom out so maybe we can see 2 pages at once. No, it's kind of awkward here. Can I change it? No. Anyways, so all these things, so this is the left side of your periodic table. All of these are metals, and then all of these are metals, and then we have our staircase here, and these are our non-metals in here. So if we had like nitrogen and oxygen, that would be molecular, and if we had like potassium and oxygen, that would be an ionic compound. So that's how we tell the difference between metals and nonmetals. And although hydrogen looks like it's a metal over here, hydrogen is not a metal. It's special. We consider it a nonmetal in things that we do. So when a substance is dissolved in water, it's called a solute, and there's 2 types of solutes. There are ionic compounds, right? Positive, negative charges from metals and nonmetals, and molecular compounds, which are made of 2 nonmetals, it says, but just made of nonmetals and share electrons between atoms. Ionic compounds will make an electrolytic solution, which means they conduct electricity, and ionic will not. And I'm going to show you why that happens. So if we take a look at this, so what we can do is we can take this salt and we can dissolve it in the water. It looks like it's dissolved in water. We can take sugar, dissolve it in water. They look the same. You don't really see anything. But if we could see this in a microscopic view, so we take this salt and we dissolve it in water, right? What you'll notice is when, before I shook it, all these were together, but when they dissolve in water, these guys break up. So the little purple ones are sodium, and then the green ones are chloride. So we have sodium and chloride, they mix around. So the sodiums are positive, the chlorides are negative. And when you have positives and negatives, they conduct electricity. So when I take, so I'm going to take my salt and I dissolve them in water, the way that we know that there's ions in there is they conduct electricity. Right? And the more salt I put in there, the brighter my light bulb glows here. Okay. So if I do the same thing with sugar, so let's remove all this. So instead of putting salt in here, I'm going to put sugar. So I put these big sugar compounds in here, and we look at them, and you can see they stay as these big compounds. They don't break up, and because they don't break up into ions, they don't conduct electricity. So if I switch to sugar, and I put the sugar in there, it doesn't conduct electricity, and that's because all these particles stay together. So that's molecular and ionic compounds. One conducts electricity, one doesn't. Other than that, they're neutral. So the first person that gave us an acid-base theory was Svante August Arrhenius, and he proposed that acids contain hydrogen atoms that formed hydrogen ions in solution. So if I took something like HCl and I dissolved it in water, it's going to make these hydrogen ions and chloride ions, right? They break up into ions, and that's why they conduct electricity. So acids conduct electricity because they make ions, right? So the fact that it has this H plus makes it an acid. So bases are the same thing, but bases contain hydroxide ions. So if I take something with hydroxide, which is this OH here, and I dissolve it in water, it's going to make ions. That's why it conducts electricity. But the fact that it has this OH makes it a base. Right? So anything that dissolves in water to make H plus is an acid. Anything that dissolves in water to make OH is a base. That's what we call Arrhenius acids and bases. Okay, so his theory works pretty good. We'll watch this video on it as long as YouTube doesn't block it. So check out this video.
The 17th century English chemist Robert Boyle was the first to study acids and bases in a systematic way. Boyle found that these two types of compounds counteract each other. Acids react with bases so that the properties of both are lost to form water and a salt. This process is called neutralization. Boyle's observations were an important advance, but he could not explain why these reactions were happening. It was not until the late 19th century that a Swedish chemist, Svante Arrhenius, made the first steps to unravel this mystery. Arrhenius found that water often could dissolve both acids and bases by separating them into individual ions. For example, hydrochloric acid, HCl, separates in water. What has happened in this reaction is that the original molecule, made up of one atom of hydrogen and one atom of chlorine, dissociates in water into its constituent H plus and Cl minus ions. The hydrogen has become a positively charged ion, or cation, while the chlorine has become a negatively charged ion, or anion. Hydrogen has only one proton and one electron, so a positive hydrogen ion is one simple proton. Arrhenius found a similar process works when bases are dissolved in water, but rather than releasing a positive hydrogen ion, it generates hydroxide ions, OH-. For example, when sodium hydroxide, NaOH, is dissolved in water, this is the reaction. In water, the sodium hydroxide dissociates. The sodium, Na, becomes a positive ion because its electron has gone to hydroxide, OH-, which is a negative ion. Arrhenius summarized his findings by defining acids as substances that release hydrogen ions, H+, when dissolved in water, and bases are substances that generate hydroxide ions, OH-, when dissolved in water. This definition explained a number of things. It showed that acids have similar properties and bases have similar properties. It solved the mystery as to why acids and bases neutralize each other. When these two substances are mixed together, the H plus from the acid mixes with the OH minus from the base to produce H2O, water. Arrhenius was also able to show that in the neutralization process, when an acid and a base are combined, they produce water and a salt. The general equation is acid plus base produces water plus salt. For example, when hydrochloric acid is combined with sodium hydroxide, a base, it produces water and an ionic compound called a salt. We think of salt as table salt that we put on food, but there are many different salts, all of them ionic compounds.
So Arrhenius theory works really well, but there's a few things that it doesn't work well for. So it said that to be a base, you need to have OH. So if we take a look at ammonia, so ammonia is NH3, but ammonia acts as a base. So for a base, we need OH minus, but there's no OH minus in there. There's an H, but where does that O come from, right? Same thing with baking soda. So baking soda can act as a base, but there's no OH minus in here, right? There's an O and an H, so maybe it has something to do with that, but baking soda can actually act as an acid too, which is weird. It can act as both an acid or a base. So Arrhenius couldn't explain that, and what we had to do is he had to modify his theory, right? It worked for 90% of the stuff, so he just modified it a little bit. And Arrhenius theory couldn't explain why some acids lit the light bulb only to a small extent. So I'll show that when we do with another simulation a little bit later. So what the modified Arrhenius acid-base theory does is it recognizes that substances like ammonia can react with water to produce OH minus. So if we have NH3 in water, so you can write water as H2O, but another way to write water is write it as HOH. And when dealing with bases, it's nice to write it as an HOH. So what makes ammonia special is on top of the nitrogen here, ammonia has these lone pairs, 2 electrons on top of there. If we saw what ammonia looked like, it has 2 electrons on top, and it's connected to 3 hydrogens like that. So this lone pair is very negative, and hydrogen is very positive. So what this hydrogen will do is this hydrogen will be very attracted to the lone pair there, and it'll actually attach on. So if we take NH3 and another hydrogen, we end up making NH4. And what this hydrogen does is it's positive, and it takes with it a positive charge. So this was neutral before. We're adding on a positive charge, so it becomes NH4+. And what's left over, right, over here, is that OH. And because hydrogen took its positive, the OH becomes negative. So what this allows us to do is it allows us to make OH minus from the water, and Arrhenius acid-base theory works again. So there were other problems with Arrhenius acid-base theory, and hydrogen by itself, if you just have hydrogen, it's basically just one proton. So a proton by itself is very unstable. So in Arrhenius acid-base theory, it said that HCl will break up into H plus and Cl minus. Well, this is very, very, very positive. And it's going to try to find anything that's negative, like water. So water is kind of like hydrogen. If I drew out what water looked like, water looks like this. And what water has is water actually has 2 lone pairs on top. So this is very, very negative. This is very, very positive. And there's always water and acid-base reactions. So this guy is going to be super attracted to these lone pairs here. And it's not going to stay by itself. So what it's going to make is it's going to make a hydronium water. So when you have water plus a proton, right, this proton is attracted to the lone pairs. There's lone pairs over here. And you make this, hydronium, H3O+. So Arrhenius acid-base theory, the modified version, says that an acid will react with water to produce H3O+. Okay, so before it was like this. Well, all we have to do to change it to this modified theory is we take HCl and it's got to react with water, right? So this H is going to be attracted to the water, and then what we're going to make is instead of H+, when this goes onto there, we're going to make H3O+. And then what's left over here is the chlorine. So it's exactly the same, only instead of H+, we make H3O+, and we have to include the water over here. So not that different. So the concentration of an acid changes its acidic properties, right? If you have a super concentrated acid, it's going to burn if it splashes on your face more than if it's a less concentrated acid, right? But the type of acid also affects the properties of the solution. So here I have 4 pictures. So this is HCl hydrochloric acid, and this is vinegar. So they have the same concentration, 1 mole per liter, right? And this is a little magnesium strip, so this is a metal. So acids react with metals, and if we look at these 2 pictures, right, this one looks like it's bubbling more than this one. So same concentration, but this acid reacts more. So let's go to a lower concentration. So same concentration again, 2 different acids. This one's bubbling, this one's not bubbling at all. So although they have the same concentration, the type of acid changes its acidic properties. So some acids will react more than other acids. So what makes one acid make the light bulb glow brighter than the other acid? So what I mean by that, let's switch to our solution here. So I can change the concentration of my acid, right? And I can make my light bulb glow brighter, right? So a really strong acid makes it glow brighter than a not strong acid, right? But what I can also do is I can change the type of acid, right? I can go a strong or a weak acid. You can see this glows brightly and this doesn't glow as bright, right? So we have to look at the acids. So all acids have this general formula. So this is the acid, this is water. So the hydrogen goes to that to make H3O+, and then the A is left over. So these ions make the light bulb light up. So with this acid here, you can see, okay, I have the A ions, these blue ones. I have H3O+ in here. So I have ions in here, but I also have a lot of these gray original acids, right? This is a weak acid here. A strong acid, if I switch it to a strong acid here, you can see that it's just ions. None of this original acid is there. And you'll notice, well, where's the water? Well, there's always lots of water. I just kind of make it hide there. But yeah, so a weak acid doesn't turn into ions completely. A strong acid does. So what makes one acid make the light bulb glow brighter than the other? Well, not all acids ionize to the same degree. So an acid that ionizes to 100% is called a strong acid. So HCl is an example of a strong acid, and that means that when we take this HCl, so say we started with 100 molecules of HCl and 0 of these. We don't have to worry about the water because there's unlimited water. And then we allow it to react for a little bit. After it reacts for a little bit, there's going to be none of these left over, and all of them will have turned into these. So that's what makes it a strong acid. All of it turns into ions. Okay, here's another way of looking at it, right? So we start off with 100% HCl. After we allow it to react, you can see that there's no HCl remaining, and almost all of it turned into ions. There's only 3 strong acids that we deal with in Science 30, and you can find them on page 12 of your data booklet. So they're the top 3 on the chart. So these are our strong acids. So if I ask you what a strong acid is on the test, just turn to page 12, find those top 3, and that's how you find out what a strong acid is. Okay, a weak acid is everything else. A weak acid will react very little in water, and only a small percentage will form ions in that water. So most of that acid molecule remains intact. So if we did an example, acetic acid is an example, and only about 1% of its molecules react with water. So if we start off with 100 of these and 0 of these, so this is a special type of acid. These are organic acids. So the H at the end here is what we care about. We can spot it because it's COOH, right? It's going to go to the water to make CH3COO minus and H3O plus. So that doesn't happen very often. After this is sort of allowed to reach equilibrium, we're still going to have 99 of these, and only 1 of them have turned into ions out of 100, right? So that's why we don't have very many ions, and that's why our light bulb doesn't glow very brightly, right? Here's another way of looking at it. We start off with all our acid, we allow it to mix in water, and we only make about 1% ions. Okay, so for this board question, I'll show them all at once. I want you to tell me, are these strong acids, strong base, or sorry, strong acids, weak acids, bases, are they ionic, or are they molecular? Okay, tell me which one they are. Pause it, see if you can name those. So this has OH. Anything that has OH is nice and easy. It's going to be a base. Okay. This one has an H at the front. Usually if it has an H in the front, it's an acid, right? So we know that it's an acid. So what we have to do is we have to go to our chart. I'm just going to go back to our acid-base chart. And is it one of those top 3? Oh yeah, there's HNO3 right there. So if it's top 3, then it's going to be a strong acid. Okay, this one here is an acid, is it a base? So this COOH at the end is those special types of acids. So this is this tells us that it's an acid. Okay, and we have to look on that chart. There's nothing with COOH that's our top 3. So this is going to be a weak acid. So anything that ends in COOH is an acid. If things start with H, they're going to be an acid as well. And then you use the chart to find out if it's strong or weak. Okay, KF here. So it doesn't start with H. It doesn't end with OH. So this is probably going to be neutral. So is it ionic or molecular? Well, we have to look. So if we go back to our periodic table, so potassium's over here with the metals, chlorine's over here with the non-metal. So it's got a metal and a non-metal. So this is going to be ionic. Okay, so this last thing here, everything that I talked about before this was just sort of an introduction to acids and bases. These are the acids and bases that we're going to use, but you kind of need to know that first stuff before we can do this. So acids and bases can be looked at as reactions where acids and bases exchange protons. So whenever I say protons, I mean hydrogen ions. So Johannes Bronsted and Thomas Lowry discovered and used this principle for their new acid-base theory. So the acid-base theory is really simple. So there's always a competition for hydrogen ions. So this is our hydrogen ion, this is our proton, right? So this hydrogen ion is always attracted to lone pairs, right? And the strength of the acid depends on how attracted it is to it. So sometimes it'll leave its mate and move to the new thing, and it's just a struggle between these two for hydrogen ions, right? Is this going to win or is this going to win? That's all that acid-base reactions are. So if you can figure out this meme, you can do acid-base reactions. So the definition of an acid that we are going to use in Sign 30 is acids are compounds which are able to donate protons. So to be a Bronsted-Lowry acid, you have to have an ionizable hydrogen atom. A base is something that can accept protons, so hydrogen ions. So to be a Bronsted-Lowry base, you must have either a lone pair to which a bond can form with an atom. So you need that lone pair. We'll talk about those situations when we do some examples. And a Bronsted-Lowry neutralization is just a competition for protons. It's a transfer between the strongest acid to the strongest base. Okay, so let's do an example. So we have ammonia and water. So we've done this one before, but we're going to talk about it in terms of Bronsted-Lowry acids and bases. So ammonia is a base. That's one that you should remember, that it's a base. And ammonia can act as a base because it's got those lone pairs on top. So this hydrogen, go back here, is going to be attracted to the lone pair of nitrogen. And when it does that, it's going to make NH4. Anytime a hydrogen goes somewhere, it brings a positive charge, and then it leaves behind a negative charge. All right, we already did that. What's new? Well, we classify things differently. So anything that accepts a hydrogen, we consider a base. And anything that donates an acid donates a hydrogen is an acid. So we classify things a little bit differently. This is an acid, this is a base. Right? We can do the same thing for hydrochloric acid and water. So hydrochloric acid is HCl, and water is like that. So water has those lone pairs on it, remember. So water is going to accept the hydrogen. Right? H2O plus a hydrogen makes H3O plus. We've done this before. Leaves Cl minus, but we classify them different. This is giving up a hydrogen, which makes it an acid, and this is accepting, which makes it a base. Okay? So like I said, to accept a hydrogen to be a base, there's only 3 things that can be a base. So if it has nitrogen on it with its lone pair, that can be a base. Another example is water. So water has the lone pair. So that can be a base. Or something like CO3 2-. Anytime you have a charge on it, that represents a lone pair, and that can be a base. So there's another term that comes up, conjugate acids and bases. So every acid has a conjugate base, and every base has a conjugate acid. The original we call the parents. And when acids give up its proton, it leaves itself with a lone pair. So if the reverse reaction happened, our former acid would become our base, and our base becomes our acid. So that might not make a lot of sense, but I'll go through the last example, and we'll add conjugate bases. Right? So when the H left, it became OH. And anything with a negative charge has a lone pair. So what can happen is a reverse reaction can happen. So this H can be given back. That's why I always draw it with a double-sided arrow, because we can go this way. So if this one's donating the hydrogen, that makes this the acid, and that makes this the base. But they're not just acids and bases, they're conjugate acids and bases, right? So we can label these in terms of conjugate acid-base pairs. So NH3 and then NH4 plus, they are conjugate acid-base pairs. The other conjugate acid-base pair is going to be water and OH minus. Conjugate acid-base pairs are always exactly the same, except one has an extra hydrogen. In terms of this one, right? So now this has a negative charge, which is a lone pair. So H3O plus can give that hydrogen back, right? This is accepting, which makes it a base. This is giving up, which makes it an acid. This is a conjugate acid, conjugate base. And our conjugate acid-base pairs, they're going to be the same, except for one has an extra hydrogen. So H2O and H3O plus are conjugate acid-base pairs. And this acid-base pair, HCl and Cl minus, right? They're the same, just one has an extra hydrogen. Those are our conjugate acid-base pairs. Okay, so I want you to do this board question, so pause the video and see if you can do this. Show an ionization equation between hydrofluoric acid and water. Label everything. So we have HF. HF is hydrofluoric acid. It's going to act as an acid, right? And then we have H2O. So it's going to give up its hydrogen to the lone pairs, right? This can't accept a hydrogen from water because it doesn't have any lone pairs. It's not nitrogen. It's not water. So this can't act as a base. So this is going to be our acid. This is going to be our base. Right? And then if H2O accepts a hydrogen, it's going to turn into H3O plus. And F is left over, so it's going to be F minus. If we want to go the opposite way, H3O plus can give that back. which makes this our conjugate acid, this our conjugate base. HF and F are conjugate acid-base pairs. H2O and H3O plus are conjugate acid-base pairs. Okay, you can also do reactions without water. So we have sulfuric acid, so H2SO4, spilled during a procedure reacts with hydrogen carbonate ion. So the first thing you have to do is figure out who's going to be the base in this situation, right? I said to be a base, you either have to have nitrogen, water, or a negative charge. So if we look at this example here, no nitrogen, no water, ooh, but this has a negative charge. So this guy can act as a base. This one can accept only one hydrogen, only one at a time. This can accept that hydrogen there, so this is going to be our acid. Okay, so if H2SO4 gives up a hydrogen, it's just going to be HSO4. And because it gave up a hydrogen, it has a negative charge. This accepted a hydrogen, so HCO3 becomes H2CO3. And because it accepted a hydrogen, it's going to have, it had a negative charge before, it's going to be neutral. Okay. We can give that hydrogen back, so this becomes our conjugate acid, and this becomes our conjugate base, and H2SO4 and HSO4 minus are one conjugate acid-base pair, and H2CO3 is our other conjugate acid-base pair. Okay, so try this one. Last question of the day. We're done after this. And see if you can figure out who's the acid, who's the base, and what the reaction would look like. So we have NH3, and we have H3PO4. Okay, so remember, nitrogen, water, a negative charge. Ooh, we have nitrogen. This is going to be our base. So it's going to give up its hydrogen there, which makes this our acid. NH3 is going to become NH4. It gained a proton, so it's got a positive charge. And then this loses a hydrogen, so it's going to be H2PO4. And it was neutral before it lost, so it's going to have a negative charge. It can give back the hydrogen, which would make this our conjugate acid, this our conjugate base. And our conjugate acid-base pairs are these two. Okay, so try the assignment. Let me know if you have any troubles.